My name is Sundar. I'm going to be talking about accelerators in container and cloud environments today. I'm a part of Intel, and the work we do spans different kinds of accelerators like FPGAs, GPUs, and so on. So in this talk, I'll be covering various aspects. I'm supposed to show this disclaimer up front. So let's start with that. As part of this talk, I'll be giving a brief introduction to what containers are, because I'm not sure about this audience, about how much you're familiar with containers. So I won't necessarily go in depth, but I'll set enough context for you to understand what we're going to talk about later in this talk. So after the brief introduction to containers, primarily Docker containers, we'll take an overview of the project which we are doing, which is called ACCE, or Accelerators in Container and Cloud Environments. We'll talk about how we abstract accelerators in general as part of this project, and how we are doing it specifically for Docker as opposed to other orchestration frameworks. So if you look at the history of how computing has evolved in a very, very brief way, initially we had the notion of running applications on physical hosts. So you would run an OS like a Windows or Linux on a physical host, and applications run right on top of that. And the general methodology or practice was to have only one application per host. Applications kind of assumed that they had the entire computer server to themselves. So this resulted in very low CPU utilization, especially as Intel made a lot of progress in adding more cores and increasing the power of microprocessors in general. So the notion of having only one application on an increasingly powerful computer resulted in lower and lower CPU utilization. However, the power consumption does not reduce just because you had only one application in there. So there were concerns about power, the footage in data centers, which are taken up by all these servers, the cost of managing these large number of servers, and so on. And that provoked the need for server consolidation. So we had various companies and technologies like VMware. Later we had KVM for x86 and so on, leading an effort to put more applications essentially on the same host, but running them on a virtual machine. So the notion of a virtual machine is that you're emulating an entire server, a CPU, memory, network, and storage. Initially started off with the emulation, but there are many other techniques involved, like binary translation and using hardware assets. But no matter which of these technologies you use, the fundamental nature of virtual machine is that you've got an entire copy of a physical server running in a virtual manner. So you got the notion of BIOS. It's got an entire OS, including the guest kernel, as well as the user space within the VM. You need to emulate or provide various devices, such as network interface cards, USB storage, and so on. So this is, of course, a full-blown virtualization. I won't talk much about different types of virtualization here, but the bottom line is that the advantage of this approach is that it's very secure, because breaking out of a VM is not easy. There have been such exploits, but they're not easy to do. On the downside, they are relatively heavyweight, because we're essentially emulating the entire CPU, memory, disk, and so on. The footprint of a VM is relatively high. And the management cost is also relatively high, because it's very easy to launch new VMs, and each of them has a management endpoint. So in the past few years, we got this notion of containers, sometimes also known as OS virtualization. A container is basically a highly simplified form of virtualization compared to VMs. You're essentially taking a process group and isolating it in a namespace and using various mechanisms already available in Linux, but they all share a kernel. We'll talk a little bit more, but basic idea is that there's this process groups which are isolated. So if you look at this picture, it kind of shows pictorially the main difference between a virtual machine and a container. On the left side is a virtual machine. On the bottommost layer is the infrastructure, by which I mean a physical server. On that, you're running a host operating system such as a Linux or Windows. On top of that, you would need an hypervisor, like Xen, KVM, or whatever. And so each virtual machine by itself runs an entire copy of the guest OS, which again could be Linux or Windows or whatever. And the application, along with its libraries and other runtime, would be running on top of that. So you've got a full software stack inside the VM. On the right side, we show a picture of a container. So if you notice, the main difference is that there is no hypervisor per se. Instead, you've got a container framework like Docker. And the containers themselves are much lighter weight because you don't need a BIOS, you don't need a guest OS. All you got is just the application by itself, along with its software dependencies. So if your application depends on, let's say, libc and let's say OpenSSL, you would actually package that along with your container. So it's relatively easy to contain all your dependencies in one package and move them about. Containers make use of prevalent or already available mechanisms like C groups, Linux namespaces. They've been around for a while. But what has changed in the past few years is that Docker has made them really popular. So because it's easy to package all dependencies together. So in your development environment, if you're tested only with certain versions, certain libraries, you can package exactly those versions. So you don't have to worry about dependency problems in the field. It is also easier to deploy because the entire container is deployed as a single image, and you can just pull that image and just run them. On the positive side, containers give you more density, and the time it takes to launch a container is also lower. On the downside, it's perceived to be less secure than VMs, but that security aspect is changing all the time because people are working very actively to improve container security in various ways. So that's the broad background. To launch a container, essentially what I'm doing in the slide is to just give just enough background to see what we will need in the ACCE project. When you run or launch a container using Docker, one of the things you can do is to take certain folders or directories in the host and make them visible to the container. So you take a host path and you map it to a particular path within the container. And you can specify whether it's read-only or read-write and so on. Other thing you can do is to pass devices in the host to the container. Yet another thing you can do is to specify what privileges the container and its threads could have. So for example, you could specify the SE Linux capability such as IPC lock, which will actually need for FPGA usage in ACCE. There are many other features. I'm not necessarily going into that here. Please let me know if you've got questions. Okay. So with that background, we're going to look at the ACCE project proper. Okay. The broad motivation of ACCE is that the data center workloads have been changing over the past maybe at least a couple of decades. The traditional workloads are like web servers, database servers, email, collaboration, and so on. And Xeon and other microprocessors in the server space were traditionally matched to that kind of workload. They did pretty well. Whereas the newer workloads are like machine learning, etc. Image and video transcoding is not exactly new, but the scale at which it's happening has increased tremendously and is a significant source of compute usage. So for these workloads, overloading Xeon with a lot of compute-intensive tasks is probably not desirable. So there's an increasing trend for using hardware acceleration. So people use GPUs, so pretty common today. FPGA is also very much being used today. You might have seen Microsoft's Project Catapult, for example. So there are a lot of interest and increasing deployments of accelerators such as GPUs and FPGAs in data centers. So, however, if you look at containers with hardware acceleration, that is relatively new. It's a kind of emerging field. If you look at the FPGAs, for example, Amazon has FPGA as a service, the so-called F1 images from Amazon, which were announced last year, support FPGAs, but they essentially run VMs. So you could launch Amazon Machine Image or AMI as a VM and associate that with the Amazon FPGA image or AFI, and thereby offload some functions from the VM to a FPGA which has been rented out. So this gives you a cost-effective way to use FPGAs in data centers. However, it's VM-based. Although Amazon has a container approach, as far as I know, they're not enabled containers with FPGAs yet. On the GPU front, NVIDIA has been active. So for example, they have a whole approach called NVIDIA Docker. They provide a Docker plugin and also a command line interface which wraps around Docker. And they also hooks into a container runtime. So there are a lot of effort which NVIDIA has put into the Docker space to make GPUs available in containers. From our point of view, one of the strengths of Intel, or one of the unique positions of Intel, is that we have several accelerated technologies available in-house. We offer FPGAs as well as GPUs, as well as other technologies such as Quick Assist. So Intel Quick Assist is a set of products and technologies for encryption, compression, and so on. So we offer several such accelerators. So it's of interest to us to bring them all together in a unified way and participate in this emerging trend of using accelerators in containers. How do we abstract accelerators? So on the face of it, GPUs, FPGAs are all radically different. They're all different from each other. The technologies are different, the products are different, the features are different. So how do we adopt a unified way to handle all of them? But if you look at any accelerator in general, what we're trying to do essentially is to pass its configuration and state to a container, right? At the most basic level, you can think of an accelerator as a device. So for example, for a GPU, typically Linux system, it'll be represented as a DRI node. So you'll typically see a device node like dev, DRI, render D64 or render D128. So this is the render node. You also have the entire card. In some cases, you can pass the entire GPU, including the control aspects, to a container or VM. There's a different node for that. For FPGAs, again, you can abstract them as devices. In addition, you may also have sys class hierarchy. So in Linux, you have the sysfs file system. Devices, drivers, etc. are represented there. So depending on what you're trying to do, you may want to pass a node or a tree in the sysfs hierarchy to a container. So these can be abstracted either as devices per se or as volumes, which are already available in Docker. The other thing you need to pass to a container is the software. So as I explained earlier, typically in a container, you would package all the dependencies in a container itself. You would not rely on the host to provide that. So if your application depends on, let's say, libc and libopenssl or whatever, you would just package that in the container. However, some things are host dependent. For example, you may have some kind of a library which depends on the hardware. So depending on the hardware version, you want a different version of the library or drivers and such. So in that case, they're essentially host dependent, and packaging them in the container would not be appropriate because the container could be launched in any host and you don't know what hardware that host has. So it makes more sense to keep the host dependent software outside the container and inject it into the container as necessary when the container is launched, depending on which host it's being launched in. The other reason you may, or other kind of resource you may want to pass to your containers is potentially images. So for example, imagine an OpenCL application running inside a container and trying to use FPGAs. One way to do it would be to package the OpenCL images of FPGA inside the container. But again, goes back to my previous point, that essentially it's hardware dependent. If you launch a different host, a different FPGA, the image package in the container may not be compatible with that FPGA. So essentially, this is also host dependent in some sense. So it may make sense to keep them on the host and inject them into the container when the container is launched. And finally, you may need to pass the accelerator configuration. So for example, in the future, let's say you're doing something like service function chaining. By the way, ACCE does not support this use case yet, but we are kind of planning for that, and we are thinking about it. So if you're doing service function chaining, the way your accelerators are linked together, how much memory they share, etc., need to be exposed to the container explicitly. So this may be done by orchestration in some way, or may be done by the server administrator in some way, but that needs to be exposed to the container. And that is the fourth element we can anticipate, which will be needed for exposing accelerators to containers. So essentially, you've got four elements: devices, host-dependent software, images, or accelerator configuration, right? So we abstract an accelerator as a combination of all of these. The bare minimum is the device, but we may add one or more of the other elements as necessary to support a given type of accelerator. In addition, we anticipate that a container may need different sets of accelerators. So for example, if you're running Nginx web server in a container, it may need, let's say, an SSL accelerator and also, let's say, a video transcoding accelerator. So it may need more than one. So we abstract the collection of accelerators as an Axel set. So that is the fundamental unit which we are structuring our Docker approach around. And to illustrate that, I'll show a couple of examples here. We'll talk more about the Intel Docker CLI in later slides, but for now, we'll just say that, let's say I got a command where I can create an Axel set. In this example, the Axel set is called WebAxel. And the -A option is saying that I want an accelerator of a particular type. And the argument to -A is GPU:any, meaning just give me any GPU on the system. So if you were to run this command, I would expect it to actually create an Axel set, which includes obtaining the necessary GPU device, preparing volumes containing needed software, if any, and also perform any tasks to prepare the device or the drivers. The other thing, the next step would be to actually use the accelerator set in a run command. So when you want to actually launch a container, you would use the run command with WebAxel as the name, which is the same name which you used in the create step. And whatever follows that are actually Docker arguments. So I'm just saying here that this is the image, the container image I want to launch, and the application I want to launch within the container is Nginx. So essentially, once I create the Axel set, I can pass that through to the container in a structured way. You could do a lot of this by hand today. You could do the device preparation by hand, prepare the volumes yourself, and do everything manually using Docker or your favorite container tool. But it'll be much more work, and also it'll be kind of hardware specific, depending on which type of GPU you're using or which brand of FPGA you're using. Your steps will all be different. So what this kind of approach allows you to do is to abstract all those details and say, I want an accelerator, and just give me one. Okay. All right. So with that background, let's move on to the next slide. So to continue this, as we said, we can demonstrate. We have separated the create and the running steps. One of the motivations for doing this is that at creation time, we may hit issues relating to the accelerators themselves. So the tasks involved in creation, as well as any troubleshooting steps, will involve accelerators. Whereas the running step assumes that the accelerator is already available. We just need to inject it to the container, So this only requires knowledge about the container and the application itself. And since we're also pre-preparing the Axle set, we are reducing the time it takes to launch a container, and there is less device dependence here. Okay, here's an example involving FPGAs to illustrate how we do it for FPGAs. So the steps involved here are that we need to pass a device. We need to pass potentially the sys class hierarchy for FPGAs, depending on which brand you're dealing with. I'm talking of Intel FPGAs here, but somebody like Xilinx may not need that. We need to pass images potentially. We need to set up drivers. In the context of Intel's OPAE library, which was open source recently, we can reasonably say that the software could be in the container itself because it's not host dependent. No matter what kind of Intel FPGA put in there, we expect that the user space library to be compatible with it. So we don't need to necessarily do that part. But when you run this command to create an Axle set, you could say that I want a web accelerator, and the -a argument option will take an argument of FPGA equal to SSL, let's say. We're saying that I want an FPGA device with SSL accelerator. And what we do behind the scenes is to actually call Docker. We're actually calling Docker behind the scenes, creating volumes and such. Similarly, when you run the run step and you give same accelerator name, we would again call Docker behind the scenes, actually running Docker run, and we would pass necessary privileges, the necessary volumes, etc. And as I said before, whatever follows the Axle set name is actually just a set of Docker arguments intact. You can just pass them directly in. Similarly, if you take GPUs, like we explained before, it's very similar. It can map the same set of steps. You got devices, you got software, you don't have images in this case, and there are no accelerator configuration sets to be worried about here. So the same framework can be used for GPUs as well. Even the way the user specifies what he wants could be similar. You could say GPU :any, or you could say I want a very specific GPU node. So there's a flexibility in terms of how you can request a particular accelerator. And this again translates a set of Docker commands. Whether it's a create step or the run step, it does the same thing. So one noteworthy feature of what we're doing is that essentially we created a Docker plugin and a CLI. The plugin which we created handles, it's basically a volume driver for Docker. And the CLI is a true superset of Docker. Whatever you can do with Docker, you can also do with Intel Docker. The reason being that if you provide the keyword Axle as the first argument in the command line, then what follows that is whatever Intel has defined. Whereas if you don't provide that, you can pass the Docker arguments exactly as they are today, no matter what version of Docker it is. Because essentially what we'll do is take all these arguments and just pass them through to the Docker CLI. So wherever you could use Docker, you can use Intel Docker as a drop-in replacement without any further change. And you also get this additional functionality by using the Axle keyword. Furthermore, if you look at what the Axle keyword provides, the verbs or the operations you provide are structured after Docker itself. So you've got create, run, ls, inspect, rm. All of these are like standard Docker operations available today. So if somebody is accustomed to using Docker, using Intel Docker, we hope, would be a straightforward step. There's not much to learn additionally. It's mostly structured along the same lines. So here's our broad architecture for how we structure Intel Docker. So in this picture, I have three kinds of devices at the bottom: FPGAs, Quick Assist, and GPU. All the blue boxes are essentially vendor drivers or vendor-specific software that's already available. So for example, if the FPGA is Xilinx device, I don't know if they support SRIOV, but assuming they do, you've got physical functions and virtual functions. And the corresponding drivers will go and claim them. So all this happens in the kernel. In this picture, all the yellow boxes are open sourced components. So you've got a VFIO driver, for example. So you could take a particular instance of FPGA or quick assist and operate that within the kernel, or could use a VFIO driver and pass it through to user space. So we are agnostic about both approaches. You could have some kind of a user space library provided by the vendor. And Intel already has one called the OPAE library, which we use. So these are already existing things. The scope of ACCE is all these red labeled boxes. So like I said before, we have the Docker ACCE plugin. We have the wrapper, or the CLI wrapper to Docker, which we talked about. And the wrapper essentially invokes Docker command, which talks to Docker daemon. The Docker daemon, as part of its operations, will essentially talk to the plugin. And one of our key approaches is that we isolate the Docker-facing side from the device-facing side. So we have a clean separation between the two. So the plugin is Docker-specific. The FPGA resource manager or the FPGA plugin or whatever you want to call it is the independent process. So it is the one who's going to actually talk to the vendor-specific library, such as OPAE library, to operate the FPGA. Similarly, you could have a GPU resource manager in the future. Right now, we don't see a need for it, and we have not implemented it. However, if there is a more sophisticated use case in the future, you could provide for that and fit in the same way as FPGA resource manager. The other feature I would like to talk about is that, as I mentioned, you could request an accelerator in the form FPGA:SSL. So you want a particular accelerator and it's specified by name. So, however, in the actual implementation, the accelerator may be identified with some kind of ID or some other schemes vendor dependent. So it translates from the name to that ID. And for that, we could provide a name server. So the name server is not yet implemented, but it's again, it fits in the architecture overall. Right now, the name server is actually kind of coupled with the plugin and the resource manager. We could separate out a separate component in the future. Okay, that's a broad approach to a Docker framework. Now, one of the advantages of this, like I said, is that it's separated the Docker side from the device side. So if you go to the next picture, let's see. So in this picture, I'm showing how we can leverage the same kind of setup or organization for OpenStack. So in this case, the FPGA resource manager is exposing one API to Docker plugin and a different API to OpenStack Nova agent. So here's how we could integrate it to OpenStack. The controller of the OpenStack is outside the host. It's running somewhere else. The Nova agent is running in the same host as where the FPGA and other devices live. There is also the host on which the FPGA resource manager runs. So the Nova agent could talk to the resource manager to discover the FPGAs and expose that, and also pass in commands and requests for specific devices or algorithms. This is the broad idea of ACCE. What I would like to do next is to show a brief demo. I'm not sure if we got time for demonstrating both GPUs and FPGAs. However, I will now go on to showing a demo of GPUs because it's a little easier to do. Okay, so as part of this demo, the first thing I would like to do is to demonstrate Intel Docker. The first step is that we're going to show how Intel Docker looks like. You just type Intel Docker by itself. It actually shows you a help text. It shows you what all things you can do with it. The next thing you can do is to list the existing accelerators. So I'm using the accel keyword here. So whatever follows that is what we have defined. They're not part of Docker per se. And this is how we're saying list all the accelerator sets you got currently in the system. And I've got these. So to show a full demo, I'm going to demonstrate what it takes is clean up everything. So I'm going to clean up all the accelerator sets. And I'm sorry, this is probably a different version. So I've not probably implemented that yet here. Sorry about that. However, we do have this set already available, so we could even create a newer one. You could use the create command, for example, to say that I want a new FPGA, and let's say I want a particular accelerator of a particular type, and that got created. And if you the interesting thing now is I could go back and look at AcceleLS. I will see two such accelerators here, my GPU and my FPGA, with volumes as needed. The other thing is I can also drop down into the Docker level. So to show that you can use Docker and Intel Docker interchangeably, I'm going to show Docker volume listing, and you can see that all the volumes we created are already available here. So you can use Intel Docker and Docker replaceably in conjunction. Now, actually, one more thing I would have liked to show is that when you actually ran the Intel Docker Accel create command, you can see what Docker volume commands it ran. So you can see the Docker volume create, the exact command is actually ran or was executed as part of Intel Docker. So this gives some transparency into what's going on here. So with that, I can now show Intel Docker. As before doing that, let me first introduce you to this thing called Intel GPU Top. I'm going to be running a GPU demo, and within that, we'll show the GPU is actually getting used. So I'm going to launch this utility. Right now you can see that the GPU on the system is not being used at all. Now let me come over here, and I'm going to just do the same step again. We got this one listed, and I'm going to run. Before running this, let me just, I have a utility script. I'll just show you. So this is the command I'm essentially going to run. So Intel Docker Accel run. The -G is actually an option which we implemented for convenience. It automates many other steps of exposing graphics device to a container, like passing the X11 socket, exporting a display, and so on. And so let's do it by hand now. Intel Docker Accel run. The Accel set we had is my GPU. I'm going to pass the -G argument for graphics, and whatever follows that is essentially just Docker arguments. I'm passing a particular folder from the host to make it easier to use it out there. And one thing is that to automate the steps of scanning a particular image, we need to identify which of those images, which of these arguments actually identifies the image. So let me first show that. Let me first show what images I have. Sorry, I didn't press the pounds. Okay, that's 1 second. Sorry. Look at Docker images. I have a bunch of these images, including GLX gears. I'm first going to show what we do for GPUs. When it comes to GPUs, here's the basic thing which the ACCE needs to do. We have different libraries for GPUs, such as Mesa, libva, and so on. So these libraries essentially are hardware dependent in some sense, because they are encoding or including the PCI IDs of the GPUs which are meant to operate. So let's say we have a particular Mesa library today, and a new version of GPU comes out tomorrow. The problem is the current Mesa would not have a PCI ID of the new GPU, so it cannot interoperate with it. So what ACCE will do is to actually check to see that the Mesa library which you put inside the container is compatible with the local GPU on the host. So let's take this example and see what happens if you try to run this command. It's actually going to say that, I'm sorry, I think I probably mistyped something. Yeah, I mistyped GLX gears. Right. So what it here was that the ACCE automatically ran Docker inspect. It's looking inside this image and it's going to do certain checks and say that, hey, here are the labels I have, and here's the GPU hardware it's detected and found what kind of GPU it's got. And it says that the version of Mesa which you have is lower than the minimum support one needed for the current GPU. So it refused to run the command, because if you do run it, either it will fail. Actually, in the case of Mesa, it will fall back to software rendering. So you will get something to work, but it will not be at optimal performance. So we catch it ahead of time and let you know that there's incompatibility between the container and the GPU hardware in the host. Whereas if you do the same thing with not with Ubuntu 14.04, but 17.04, it works differently. This actually would have, okay, here, I'm inside a container right now. We know inside a container because if you can see Docker and here, so we know it's the container. I'm going to run an example command. I believe the syntax goes like this. And you can see that GLX gear is not only running, you can see that the usage of GPU has increased slightly. It's not taxing the GPU at all. If I run more instances of GLX gears, you will see higher percentage usage. Similarly, I can also demonstrate running VA API inside a container, but that will take a little longer time. I believe I have only about a minute or so left. So in the same way which we launched the Mesa image, you could launch separate image for containers which runs VA API. You can demonstrate that the VA API version is checked against the local host hardware. We just need to do LSPCI to identify a kind of device and check that out. If there is interest, I can go into that also. But right now, what we have shown is that here's GLX gears. And by the way, I could do the same thing maybe in a different host as well. So let me do interlocker axle run my GPU -g --rm -it and then I have to specify the image, which is GLX gears Ubuntu 17.04, and I'm running this, and I could launch another instance of GLX gears, and you can see that the GPU usage probably will go up a little bit. You can see that the moment it's launched, the GPU usage kind of increased a little bit. In case you guys missed it, here's the live demo of the GPUs. GPU running a container. So I'm running GLX gears inside a Docker container. We have a couple of those windows running, and you can see the GPUs getting used using Intel GPU top to show that. Okay, the first question is what are us under duties using the solution in industrial IoT. What we have aimed this one is primarily at data center usage. So this allows you to use GPUs generically in containers without reference to what kind of workloads you're running. So for whatever reason you use GPU, you can use that. If you want to use FPGA, you can do that. So what we're enabling is that you could use the accelerator of your choice in a convenient way without knowing too much about the hardware details. The hardware details are abstracted by the device plugin and also by the fact that you got a convenient user interface, where you don't have to specify the exact device node or accelerator ID, but instead use strings and names. Okay, how does solution relate to Kubernetes? Very interesting one. So what I presented today will not work for Kubernetes because the plugin we wrote is a Docker plugin. In Kubernetes, there is a proposal in the community to standardize devices. We are participating in the community. The current APIs being proposed in the community fit FPGAs to some extent, can support some use cases, but not all. So what we are trying to do is to do some kind of approach where we see what changes are needed for supporting FPGAs in Kubernetes. Okay, so that's an independent track. The Docker plugin, which I demonstrated today, is not meant for Kubernetes. We'll try to separate device plugin for that. In fact, we'll try to separate device plugins for GPUs and for FPGAs. What is the competitive differentiation of the solution? If you look at NVIDIA, for example, they make it very easy to use their GPUs in container environments by hiding the hardware differences to some extent. We would like to be in the same space, and we believe we can enable that. In addition, if you look at FPGAs in container environments are not that common today. There's interest in them, but it's not standardized. So what we are providing is a way to access FPGAs in containers in a neutral manner. So this makes it easier to use any Intel accelerator. So if you're interested in the combination of different technologies, you can use Quick Assist and GPUs together, for example. In the future, if you have, let's say, smart NICs based on FPGAs and also Quick Assist, you can use them all together. So there are different aspects to it depending on which side you're looking at, GPUs or FPGAs. But basically what we're doing is getting all Intel accelerators together in one place and make them very easy to use and deploy. Is there any way for developers to prototype the solution for smaller tasks, then scale to bigger solutions? Okay, I'm not sure what I mean by smaller task and bigger solution here. But if you are launching, let's say, a single container, it's very easy to do that. The way we have done it is easy to integrate Docker Swarm as well. Kubernetes is a different story, but you can scale to a larger number of containers and more devices by using some orchestrator like Docker Swarm. So since it's part of Docker infrastructure, we don't expect any issues in this deploying more containers and devices using the same approach. Okay. Thank you all. Thanks for patiently listening to me. You can ping me by email or any other available means after this talk if you're interested in knowing more about this. Thank you so much.